I am really excited about this next talk. This next speaker is a software engineer and PhD researcher who's bringing Unison into the domain of AI. But this is a very friendly introduction to backpropagation in neural networks, and it's a great primer into something that can seem quite mysterious. So please welcome Gerard Finol.
Thank you, Rebecca. Okay, let's start. Okay, yes. So today's topic is backpropagation in Unison, and I'll try to do a friendly introduction. So first of all, just a quick about me. I'm a mathematician and computer scientist. I did the bachelor at University of Barcelona. Currently doing the PhD in Cloud Lab at University Rovira i Virgili. My research is focused on cloud computing and streaming computing, and more or less that's me. And today's plan is just to talk about neural networks. We'll talk about what's a neural network, how do we train neural networks, and we'll explain the role of backpropagation when we train neural networks, and we'll finish with some Unison code and Unison demos. So I'll start explaining the idea behind neural networks and how do we train neural networks. So I put these slides at the beginning of the talk because it's like an easy example that I want you to keep in mind during all the talk. So you have to imagine that you are in a mountain, so in a two-dimensional mountain, and that you are a beach ball. So you are here, and your goal in life is to move as low as possible in this mountain. So you want to go, let's say here, down the mountain. So if you are in this position, if you are here in the top of the mountain and you want to go down, you just need to follow the slope of the mountain and do small steps, one after the other, following the slope of the mountain until you reach the the end of the mountain. So more or less that's the idea, and this is how uh, training neural networks work. Like when we train a neural network, we're doing something like this. So I want just to keep this in mind. So once we have this quite clear, let's see what is a neural network. So maybe some of you think that a neural network is just a big black box with some inputs that produces some outputs. For example, if you have a neural network that you feed with a cat image, the neural network will tell you that there's a cat in the picture. So more or less that's the concept of a neural network, and we don't need really much to know about them to know about backpropagation and how do we train them. But I'll mention some extras. So what we need to know also is that at the end of the day, a neural network is just a big mathematical function that has some inputs, some parameters, and that produces some outputs. Um, for example, here the picture of the cat, it's the input, so it's x will be the input here in blue, and we have in red y, that will be the vector of probabilities. To, like for example, this is the probability of having a cat in the picture, having a dog, and so on. And the neural network has the parameters that we mark it with the double B, that we'll see later what are they. So typically a neural network is represented like this. We really don't need to know all these things that come. We just need to know that it's a big mathematical function. That, but I mentioned some extra details just to be sure that everything is clear. So we have this representation. Each circle it's called a neuron. So we have a neural network. So we have neurons, and each circle it's one neuron. We have the neurons are structured with layers. So here we have the input layer, that's this one. We have the hidden layer and the output layer. In our input layer, we feed just the just the input, so the x. So in the previous example, that's the raw pixels of the image. In the output layer, we obtain the output, just for example, the probabilities in the previous example, and the hidden layer, or the hidden layers, because there can be multiple layers hidden. We have just mathematical functions. For example, this neuron that has like some parameters that it's different from this one because it has different parameters and so on. As I said before, we can have multiple hidden layers, but here in the representation there's just one, but you can have as many as you want, of as many as your computer or your cluster can work with. And just one last thing to know about the neural networks is that we have these layers. The output of the first layer is the input for the next layer, and the output for the hidden layer is the input for the last layer. So we are feeding the input of one layer into, so we are feeding the output of one layer into the input of the other. So we, at the end of the day, we are doing function composition. So that's a topic that we all know. If we are doing functional programming, we know about composing functions. So we are more or less at home. So we have a big mathematical function that's just the result of the composition of a lots of functions, smaller functions. That's more or less the definition of neural network that we'll be using today. And about the parameters of the function, I'll talk about what they are. So parameters of of a neural network work like just like dials in an audio mixer. If we have an audio mixer, then we feed the voice or the guitar sound to the audio mixer. We just change the parameters and we until we find a good setup for our voice to produce a good output song. So more or less that's the role of the parameters is just to change how do we treat the input to produce a good output. So when we train a neural network, we are just finding the parameters that produce the best possible output, or at least the best possible output that we can find. So what are good outputs or the best outputs? So more or less, we already we all know that if we have a picture of a cat and we expect the neural network to tell us that there's a cat in the picture, and that's a good output. But if we have a picture of a cat and the neural network says that there's a dog in the picture, that's a bad output, more or less. We know that. So when we train a neural network, we need a way to measure how our neural network is doing. So we need an error function. The error function or loss function or cost function has different names. This error function just measures how good or bad the neural network is doing its job. So if we have a neural network with a picture of a cat tell us that there is a dog in the picture, the error will be higher, and if it tells that there is a cat, the error will be smaller. So the best outputs means that we have the smaller error possible, and when we train a neural network, we want to go to the smaller error possible. So here we see more or less the correspondence with the thing of the mountain and the beach ball and so on. So we want to go to the smaller error possible. That will be our mountain. So the error function is just the mountain in the metaphor of the beach ball. The parameters are the beach ball. So we change the position of the ball. We change the parameters of that fit the model. And the slope of the mountain is just the derivative of the error function. So when we were moving through the mountain to find the lowest point of this mountain, we just following the slope. That means that we follow the derivative of the error function. So when we want to do a mountain descent or going down through the mountain, we just do like the next position of the beach ball will be the current position minus the mountain slope multiplied by some small number, just to be sure that we are doing small steps. We want to go little by little, so we put here like 0.001 or something like that, and we follow the slope of the mountain. So translated this into the error function, that means that we have the next parameters. So the parameters at the iteration n+1 will be the previous one. So the parameters are at the stage n minus this lambda that was the small number, just to do small steps, multiplied by the derivative of the error function evaluated in the previous parameters. So the slope of the mountain. So we can come back to the metaphor of the beach ball and see that yes, we are here, we measure the slope of the mountain and we do a step. We measure the slope of the mountain and we do a step. And we measure the slope of the mountain and we go step and we arrive. So that's more or less the idea of training neural networks. But we normally we are not in a two-dimensional world. We we live in a three-dimensional world, and our parameters do so, or at least three-dimensional world. They can be higher dimensions. So if we have 2, 3, 4, 6, n parameters, we will have like 2, 3, 4, n dimensions. So we will have as many dimensions as number of parameters that we have. So when we have higher dimensions, we can things change a little bit. So I'll do an example with a 3D mountain because I can show you a 4D mountain right now. So we are here at the top of the mountain and we do more or less the same. We measure the slope of the mountain and we follow the slope of the mountain and we do a step and we move. We continue doing the following the slope of the mountain and we do a step, continue and we do a step. And here notice that the slope of the mountain changed because we arrived to a valley. So the slope of the mountain now it goes to the right. We cannot continue going to the left because we will going up. So we want to go down. So we go to the right. And we continue doing the same. We look at the slope of the mountain and we follow the path. That's the idea that I want you to have in mind, that we take the slope of the mountain and we follow that. That's everything. So notice that when we follow the green path, not the red one, because we follow the slope of the mountain. That's the song that I want you to learn. So here, the slope of the mountain, it's not the derivative of the error function, because when we are in higher dimensions, we cannot compute the derivative. We use the gradient. So the gradient, it's a vector that has if we have an n dimension parameters, so we have n dimensions, we have a gradient that has n derivatives. And the derivative, the first one is the derivative of the error function with respect to the first parameter. The second one is the derivative with respect to the second one, and so on. So in higher dimensions, the gradient will be our slope to follow. So when we apply the formula, we change the formula and we change the derivative that we had in the two-dimensional version by the gradient, and we have that the gradient descent. That's what it's called. We have the same as before. We have the next parameter position, or the next beach ball position will be the previous one minus a small number to do small steps multiplied by the gradient. So that's how we train a neural network. That's all the magic that's happening. So we need we already know the parameters. We can do multiplications and we can compute this, but we need a way to compute the gradient of a function. If we can do the computation of a gradient of a function, we can implement the training of a neural network. So here it's where backpropagation comes to the rescue. Backpropagation is an algorithm that is used to quickly compute derivatives. And as I said before, the gradient of the error function or any function is just a vector with n derivatives. So if thanks to the backpropagation, we can compute the gradient, and as we can compute the gradient of the error function, we can update our parameters and train the neural network. So before explaining backpropagation, I'll do just a small calculus reminder. I'll explain the chain rule. Okay, so the chain rule is just the only formula that I will not more or less explain why that happens, but you have to trust me that it happens and it's true. But I'll just explain that. So we have the chain rule that it's a formula that will allow us to compute the derivative of a function that is the result of the composition of two other functions. So here we have a function f, a function h, and a function g. And f is the composition of h and g. So the chain rule says that the derivative of f is equal to the derivative of h evaluated in g of x multiplied by the derivative of g. That's all. And remember that a neural network is just a big mathematical function that is the result of the composition of lots of functions. So more or less everything has sense. So we more or less we have like all the tools to do the things. I'll do a small example of the chain rule just to know that everyone is on the same page. So for example, here we have a small function, a simple function that is 3x squared, and you can observe that the f function is just a composition of these two functions, the x squared function and the 3x function. So when if we want to compute the derivative of f, we apply the chain rule. So we first compute the derivative of g and the derivative of h. So here we have 2x and 3. That's the derivative, and we also can compute the derivative of h evaluated in g of x. That's 3. So we can apply the chain rule, and we just obtain that the derivative of f is 3 multiplied by 2x. That's 6x. And more or less that's the chain rule and like the formula that we'll be using in backpropagation. So let's see how backpropagation works. We have the main idea is that we build the computational graph of our function and we evaluate the function going forward in the computational graph, and we save the intermediate results for the computational graph. We store them. Once we arrive to the end of the computational graph, that means that we evaluated the function. We have to go back. That's why it's called backpropagation. We have to go back applying the chain rule and propagating the derivatives. So that's why it's called backpropagation, because once we go forward, we have to go back and propagating derivative, and we can enjoy our gradient. So let's see an example. Here we have the function f of xy, that's x squared plus xy minus 3y. And here we have the computational graph of the function. Okay, we have x and y, the square, the multiplication, 3y, the addition, and the subtraction. That's the computational graph. So the first step is just to evaluate the function. So we will be evaluating it in x equals 4 and y equals 2. And we start doing the forward steps. So we start with x and y, we do some more steps, and we keep doing the computation, and we arrive to the end, that's 18. Okay, we evaluated the function, and now we can go back. We have to go back propagating the derivative. So we start here at the end, and we go we do one step, and we compute the derivative of this node. Okay, so just a small hint, I put names in each of these operations just to be able to reference them. So this is b1, b2, b3, b4, and b5. So we want to compute the derivative of b5 with respect f. Derivative of f with respect b5, sorry. So here we have the derivative of f with respect b5 is 1 because the result of b5 is just the same as f, so it's the same. It could be the same node. And this will be always b1. You'll see later in the code, it'll be much clearer, but you'll see later in the code that when we do the backpropagation, we start with 1 because always it's 1 because the last point it's always the same. So here we have always the same 1. And we go back. We go back to 4, the before, and we'll propagate this derivative. So here we compute the derivative of f with respect the before, and here it's when the chain rule enters in the game. We have the multiplication of the derivative of f with respect b5 multiplied by the derivative of b5 with respect b4. That's the derivative of b5 with respect b4. Okay, so the first element of the multiplication we already computed. It was 1, so that's the easy one. And that's why we call propagating, because we are passing the derivative of the previous stage to the next one, and we propagate it. And here we have the derivative of b5 with respect before. It's -1. Why is -1? Because we have here a subtraction, and the derivative of the subtraction is -1, so we pass a -1 over here. So we just say that 1 multiplied by -1, and I write it here, the result. So our next step is y. So we'll be computing the derivative of y, the derivative of f with respect y. So here, and we are applying the chain rule. So this is the value that we computed previously. So it's -1, and here it's the derivative of before with respect y. It's just the derivative of this function, that's 3, multiplied by y, that is just 3. And what we are doing here, we are accumulating the gradients in the variables. That's an important step that I didn't mention, so I mention now that when we arrive to a variable, we accumulate the gradients that we obtain. So because will be arriving to this variable through two paths. That's the first one, and when we come over here, we'll arrive to y another time, and we'll just add the gradient that's been propagated through this path. And you'll see later in the code, it's much clearer that we are just accumulating the gradient in the two variables. So, and the rest of the algorithm is the same. So yeah, we have the -3 and just save it here. The rest of the algorithm is the same. We just applying the chain rule and keep computing the same. So for this one, just applying the chain rule, and we have that the result is 1. We write it here. We do the same here. Apply the chain rule, multiplication. It's what it's been propagated, the same 1, and here the same 1. And we arrive to x. And for example, we came from here. We have this is what is being propagated. It's 1, and this is the derivative of the function x squared. That is just 2x. So we evaluate it with x equals 4. That's 8, and we write it here. And the same when we came over here. We just apply the chain rule. That's what has been propagated, and this is the derivative of the multiplication. That's just the y, and we evaluate it. That's 2. So we, as I said before, we accumulated. Now we have 8 plus 2. 8 that was the result before, and 2 is the result that we have now. So 10, and we update it. And we do the same with this way. That's the derivative of the multiplication with respect y, just x, and we set 4, and we update it's -3 plus 4, 1. So we computed the both derivative. They are the elements of the gradient. So we computed the gradient of the function f. with respect x and y. So that's more or less the idea. And now let's see how this is implemented with some Unison code. Okay, so that's the code in Unison. I start with an expression type that's just AST that has the operations, just addition, subtraction, multiplication, and so on, and the variable. The variable just has the text field. That's just the name of the variable, so x, y, or z, or whatever. And another example, another type, that's just the evaluated expression, that it's the same as before, but I have the float, and here I'll be saving the evaluated graph. So this this will represent the graph without evaluating it, and this will be created once we evaluate this graph, and I'll be storing here the value that it's been computed. I have some auxiliary function get value that just returns the value from an evaluated expression, just a pattern matching. Oh, oh, sorry. Okay, just sorry. Okay, now you are using the code. Nice. Okay, I'll repeat it. Here I have an expression type. That's that builds the IST for the computational graph of the neural network. So we have the addition, the subtraction, multiplication, constant, and variable. Notice that the variable has a text field, and that it's the name of the variable. I have also the evaluated expression that has it's the same as before, but with the float field that will be saving the intermediate value. So this will represent the computational graph before evaluating it, and this will represent the computational graph once has been evaluated and with the intermediate values saved. I have a get value function that gets the evaluated expression and just return the value. So the float, it's just a pattern matching that gets the value and just return it. So it's quite simple. And I have an ability. The ability just has this effect that's evaluate that gets the text of the name of a function of a variable and returns the value of the variable just to evaluate variables. And I have an expression, yeah, a function that gets an expression and returns an evaluated expression. So it's a function that evaluates the expressions. So for example, if you have a constant, I just return the evaluated constant with the value. Just it's an easy one. If we have an addition, we have with two expressions. We are adding two expressions. We first evaluate the first expression, evaluate the second one, and we just return the value here. That will be the value of the first one plus the value of the second one. And here I just return the evaluated expressions also in the field. And the subtraction and multiplication are the same, just changing the operation that you return the value. And I have the variable case that I just call the evaluate bar from the ability before. And that's all. That's how we evaluate our computational graph and save the intermediate values. Here I have the function that just receive a map that goes from text to float. That's just the names of variables and the values of the values of the variables that we want to use, and it just gets the values from the map and returns it. So it's an easy ability handler. And here I have a small example of an expression. I have this expression 3 plus 2x. I have the constant 3 that's the first parameter of the addition, and the second one is the multiplication of 2 multiplied by the variable x. And I evaluate it. So I just save the document to execute the watch expression, and here we have that the result is 7. So far so good, because 2 multiplied by 2 it's 4 plus 3 7, so we are good. So we have like the first part of our backpropagation algorithm. We have the part that is going forward. Now we need to implement the part that is going back. For that, I have another ability, that's the derivate ability, that has two functions, two effects. So the accumulate derivative, that just receives the name of the variable and returns the float, and the get derivative, that gets the name of the variable and returns the what's being accumulated. Sorry, here we have the text of the variable and the value that we want to accumulate, and it accumulates. And here we got the value that's being accumulated, and here it's just the implementation. As we see here, we just have a map, and we get a value. We just update the map with this value. We get the value that was before in the map, and we accumulate it, and without the default of 0, and we update the map, and we follow with the new map. We resume with a new map, and if we want to get the derivative, we just get the value from the map or with a default of 0 and continue. So now the backpropagation algorithm. Here we have the input, that's an evaluated expression. So we have the representation of the computational graph with the intermediate values, and we just implement the previous algorithm. So we have a loop and an accumulation. The accumulation is the propagation of the derivative. So for example, if we have a constant, we just do nothing, because we know that the derivative of a constant is 0, so we don't have to propagate anything. If we arrive to a variable, we just call the accumulate derivative with the name of the variable and the accumulation field. And if, for example, if we have an addition, we go through the first one and we propagate what's been accumulated. We propagate it without changing it, because the derivative of addition is just 1. So here it's in reality it's 1 multiplied by accumulation, so it's just accumulation. And the subtraction, it's more or less the same, but if you notice that when we propagate through the second expression, so the one that's after the minus, we propagate minus the accumulation, because as I said before, the derivative of the subtraction is -1, so we multiply the accumulation by -1. And the multiplication more or less the same, but we just propagate the value of the other expressions. So if we have, in the first expression, we will propagate the accumulative multiplied by the value of the second, and the other way with the second expression. So that's the backpropagation algorithm. That's quite easy to implement, and we'll just run with an example. We have two variables, x and y, and this expression that's set. We evaluate the expression set, so we have here the evaluated result, and we fit this into the backpropagation function, and we call get derivative for the variable x and get derivative for the variable y, and just return the gradient, that's both derivatives. So I'll just save another time the code, and okay, here we have that 7 and 8. That's if you do the math here, and you apply it in this point of the function, you will see that's 7 and that's 8. Okay, so we have the backpropagation algorithm working. Now I'll change to my slides. Just confirm me that you are seeing the slides, please. Nice. So now, as the final result of my talk, I'll just show how to implement a small neural network. This neural network will be a simple neural network that will just tell us if a person is under 18 years old or if it's over 18 years old. So the input of this neural network will be the age, so just one number. We'll have only one neuron, that will be applying this function that's called sigmodify function. And we have two parameters. We have the WB1 that will be multiplied by x, and we have WB0. And the output will be a number between 0 and 1. 0 will mean that the age of the person it's under 18 years old, so it's underage, and 1 will be that it's over 18 years old. So let's go back to the code, and I have here the same. Okay, here I have the same expression, but with some extra arithmetic and some extra operations. Here I have the evaluated expression just as before, but with the new ones, and it's all the same, the evaluated, the variables, but with the new cases in the pattern matching. The evaluated expression also with the exponential, division, and logarithm, and the derivative the same. So, and the backpropagation the same. So we have here the implementation of backpropagation for these cases. So I have the negate function that just gets an expression and returns the negation of this one. So it's minus the expression. I have the sigmoid function. That's the one that I explained, I showed before. That's just the exponent that uses the exponential and the division. And I have the implementation of the neuron that just do the multiplication of the parameters and the addition. So here we have the parameters with x and so on. And we pass this to the sigmoid function. That's our neuron. And I have the error function. That's what we are going to use to train the neural network. That's the here received two expressions. One is the true value or the expected return value of the neuron, and the other one is the current return value. And I just do the subtraction and compute the square. And we can train a neural network with this. So let's do it. I define the variables. I create the neuron with the neuron function, and I just compute the error with the variable and the output of the neuron. I create a small data set that will be just the ages between 0 and 100, and the tag for this dataset, so the correct answer just will be 1 or 0 depending of the value of x. And I get some initial random weights for our neural network, so initial random parameters, and we'll do just a loop. The loop will be just the updates of the initial parameters. So we'll do count iterations. So and the loop is just picking a random element from our dataset. We evaluate the neuron and we compute the error. So we compare with the y value, and we compute the gradient for our parameters, and we do the gradient descent update process with here. Say that we have the 0.1, so small steps, and we do the next iteration, and we do this for 10,000 times. 10,000 times. So I'll just save this file and I'll do the run main. Okay, here we are just doing iterations, 10,000 iterations, training our neural network. It just takes some time because I'm sharing the screen and my computer it's quite slow. So we obtain the values, and we'll finish just evaluating the neural network with these two values that are I just write it here. So we evaluate it, and I print the output of the neural network for all the ages between 0 and 30, and we'll see what happens. So we'll run this function. So here we have that for an age of 0 until an age of 17, all the return values are really close to 0. I mean, it's almost 0. And from 18 to 29, they are really close to 1. So our neural network has learned to differentiate an adult data from a baby. So that's all that I have for today. Thank you very much. And the code of the talk will be here published really soon. And here you have the QR code from this link. That's everything.